is Dr. Pascal Elahi. I'm the Quantum Supercomputing Research Lead at the Pawsey Supercomputing Research Centre, and I'm here to chat to you today about enabling hybrid quantum classical computing. Now, before I begin, I'd like to acknowledge country. So I'm based in Australia, specifically Perth, and I would like to acknowledge the traditional owners of this land and where I'm coming from, the Noongar Whadjuk people, their ancestors and elders past and present as the regional custodians of their land. In their language, Nangalik Kadich Noongar Mut Kayan Kadich Nijapuja. So, what is Pawsey? Well, it's the National High Performance Computing Centre headquartered in Perth, in Western Australia. It was launched in about 2014, but the foundations of Pawsey date back to about 2000. It employs over 60 staff through the National Science Agency of Australia, CSIRO. But critically, Pawsey is a supercomputing centre that tries to be at the cutting edge of technology, and the domain is scientific computing. We accelerate discovery through world-class supercomputing infrastructure and expertise. We do this by providing not just high-quality supercomputing infrastructure, like Cytonix, our supercomputer that has about 45 petaflops of computing power, but also lots of storage and expertise. And this supports over 250 science projects from Australian researchers, with about 4,000 of them, using the various services and systems provided by Pawsey. We train about 10,000 people a year as well. Now, this leadership role is well acknowledged and recognized. We have helped researchers attain national recognition, such as the Australian Prime Minister's Prizes for Science. Dr. Anzu Horsley, who's one of the founders of Quantum Brilliance, did quite a bit of initial work with Pawsey. And there's even global recognition. So Professor Giuseppe Barca led a project out of ANU and the University of Melbourne before, where he upscaled his code and his code base access to run on GPUs, and they actually won the Gordon Bell Prize for their groundbreaking quantum molecular dynamics simulations. It's not just performance in science we help support, but we also are very active in the diversity and inclusion. We're trying to ensure that internship programs, for instance, have a high fraction of women taking up these roles. 25% of the staff at Pawsey are women. We celebrate Harmony Day, and we've actually been recognized with a number of awards or nominated for awards with Women in Technology Awards of 2004. Myself and Aditi, who's another Pawsey staff. And in fact, Pawsey leads some of the Women in HPC events because Aditi is one of the major chairs. Now, to the quantum computing. So Pawsey received a government grant to start looking at quantum computing and integrating it. And this led to the launch of the Quantum Supercomputing Innovation Hub. Now, this hub, powered by Pawsey, serves as a collaborative platform focused on integrating quantum computing with classical scientific computing. The idea is, again, to accelerate scientific breakthroughs by providing all the research, the infrastructure and expertise necessary for researchers to make use of new computing technologies. The Quantum Supercomputing Innovation Hub is founded on 3 pillars: innovation, education, and inspiration. I'll take the last first. So inspiration, we do outreach programs. Education, we are not just involved in outreach, but actually help supervise PhD students, provide them access to infrastructure, and also provide expertise. And innovation, we also develop in-house software, but also have helped other groups deploy hardware. So example I mentioned before, Quantum Brilliance is actually a world first room temperature deployment in a data center of their QDK, their quantum development kit, way back in the early 2022, 23, and continued on. So we really try to foster innovation as well. Now, about enabling hybrid quantum computing. Well, I'm going to break it down to 3 sort of projects that we're looking on to, but I want to introduce the team that's leading some of this work. So on the picture to your right, you have myself, but you also have the other team members, the quantum researchers that are involved in the Quantum Hub. Shu Sen, Edric Casey as well is part of Pawsey, though he's now also fully a UWA as a senior lecturer, so University of Western Australia, and our director and CTO, Ugo de Vereto. So the 3 sort of pillars I'm going to chat about in terms of the enabling quantum computing is virtual QPUs and HPC quantum simulation. So really making use of the HPC system as a QPU to test stuff, to do technological development, looking at new types of quantum hardware, characterize existing quantum hardware. Then I'm going to talk about quantum virtualization, specifically QPU virtualization for job parallelization, job stitching, and so on. And then I'll chat about the integration layer, which happens to be called QBitBridge, looking at coupling the HPC system to the QPUs. Now let's dive into quantum simulation. So it's a critical aspect of developing quantum algorithms is actually simulating them, because the current devices that are available might not be necessarily ready. And so in this vein, we've developed an in-house quantum simulator that is GPU agnostic, that scales well both on AMD GPUs and NVIDIA GPUs. The reason we do this is that Cetonix is an AMD MI250X system, so lots of AMD GPUs, but we do have a few GraceHopper nodes, superchips. So we want to make sure that we have portable and code that can go on both platforms. It's HPC native, so it's got MPI integration at the base, and it's has also some future proofing that we're trying to add in a large leverage unified memory systems, such as GraceHopper superchips for massive simulations. It's competitive with other code bases out there. So if you look at the runtime of certain sets of circuits, you can see it's actually quite fast in some aspects. Not all circuits, but like most circuits can be very, very fast. It can actually beat Qiskit Air, which is a industry standard for performant HPC simulation of quantum circuits. It even does a little bit better in some cases than Qiskit Air with the Q quantum backend. So this is specifically running on GraceHopper superchips. But also this performance, though it is not as performant on the AMD systems yet, we are still trying to improve the performance, but it does run on those GPUs. So there's a nice unified framework. And critically as well, it can run noise models. So there's smooth noise injection of specific sets of noise models. And that's very critical for the current ecosystem that quantum computing devices live in. So they are NISQ devices, the noisy intermediate scale quantum error. And so characterizing the noise and being able to model the noise is critical for understanding whether an algorithm can run on a given bit of hardware. And on that note, not only do we want to have HPC simulation of quantum circuits, but we would like to abstract this HPC simulation as a virtual QPU. The reason why is there's a misalignment between how supercomputers are accessed and most people's interaction with QPUs or quantum computers. Right, supercomputers are accessed through batch scheduled execution environments, and quantum computers are typically used through interactive device-oriented semantics. So we developed this two-plane system. So there's a control plane and an execution plane, with the idea of the control plane being a cloud-facing control plane where people are going to interact with submit circuits to check the validity of those circuits. And the execution plane is an HPC-resident execution plane that presents itself as an agent for running simulation with several devices listed. And this means that we enable HPC quantum simulation with specifically device-faithful simulation, right? Because we can provide noise models, but it also allows for exploration of new quantum architectures with novel topologies and noise characteristics. So in this diagram, right, critically the control plane is authoritative in the state of a particular simulation, and the simulation is not just a quantum circuit simulation, but is specifically tied to a device snapshot. So you run a quantum circuit on a given device with a given connectivity and a given noise model, and it will then have this task presented to be claimed by execution plane agents, right? So these agents can be on a couple of different HPC systems, and they will claim, so it's a pull rather than a push into the execution plane, so keeping the security up of the HPC system, and report back that it's alive, and then eventually once it runs the simulation on the system using the job orchestration tools present on the system, such as SLURM, report back and give it the control plane a snapshot of what was run and the results, right? So it's a real contract of saying, I'm going to run this circuit on this device. And that means you can really start playing with introducing new devices. So if I give a view of the VQPU, this HPC-enabled VQPU, these are just snapshots of the cloud interface. specifically NVIDIA view. But what I want to bring your eyes to is the actual device that can be run. So you can actually upload and edit a device snapshot, which can have a noise model. So you can have calibration data that's constantly updated. A specific connectivity, there's T2 times and T1 times for a given qubit, the number of qubits. This allows you to faithfully recreate existing devices, but also propose new devices with new different types of connectivity and topology and noise models. Then, as a user, you can submit a circuit and run circuit and look at the various bits of infrastructure that are running. So here's an agent running on one of our non-production systems, Ella, with all the various services that are necessary to run this and have a payload be deposited at the cloud interface. So this is quite cool because it's not just oriented for virtual, like making the HPC system look like a QPU, but really enabling the HPC to look like a wide variety of devices and enabling device exploration. On top of that, we're looking at advanced compiler strategies. So DynQ is a compiler. It's more of a virtualization of a quantum computer, because the idea here is through a quantum virtual machine, you can do aggregation of execution and segmentation of execution. The idea here is that a QPU, for the aggregation process, is even a large QPU chip. You may have many small tasks. So you don't want to underutilize the QPU. There can be very common cases of this in terms of GPU, right? And there are lots of big GPUs now, and there's lots of codes that make use of GPUs to their fullest, but there is codes that are out there that have a low occupancy of the GPU. The same can be said for lots of circuits that people are running. If you consider some of the larger systems that are available with 100-ish qubits and the typical things that people can simulate, and so then tend to also submit to see how the simulations proceed, that's maybe 20, 30 qubit range. And so you would have a vast underutilization of resources. So by looking at seeing if you can aggregate lots of different tasks and place them, noise-aware placement, I should point out, then you can manage the crosstalk between parallel processes and get a higher utilization rate. The same thing can be said for segmentation. If you have a larger circuit, then you can break it up into a bunch of smaller circuits that then run on multiple small chips. This decomposing allows you to exceed the current device capacity of a QPU. Now, I should mention that this idea of circuit knitting and parallelization and segmentation is still a work in progress, but the aggregation is fully operational within DynQ. Now, it would be not enough to just have a QPU be able to, let's say, aggregate and take up small atomic regions. There are lots of devices, specifically if you're thinking of superconducting systems or even spin qubit systems, they're quite heterogeneous in terms of the qubit quality, right? So, and they drift. So there's device drift. You might calibrate your devices and your qubits, but then if you wait enough, there's enough drift on the device that you have to recalibrate. So you have this setup that needs to be dynamically polling the setup and figure out which regions of the QPU are optimal for certain circuits and maybe other ones that are poor, right? And this is really a new frontier, which is we've worked on looking at a device community detection on a device to figure out atomic regions that can undergo high fidelity computation. So here's an example of that aspect. And I should point out that the detection of atomic regions, or this community detection, isn't fixed to any topology. It's topology agnostic. All you need is a connectivity graph with fidelity measurements. You can use T2 times, T1 times, the single qubit, 2 qubit fidelity measures. Currently, we focus on 2 qubit fidelity measures to identify regions in which there is high fidelity of qubits, and then segregate the system into atomic regions that can perform at high fidelity a quantum circuit. I've shown that IBM's heavy hex and Rigetti's grid systems that happen to be Anka and one of the Heron chips. The idea here is that you can see that there's different multiple sets of regions with different numbers of qubits. Some of them are small, but most of them try to be quite large. And in that region, you actually have a minimal crosstalk outside, minimal crosstalk inside. So there's high fidelity and there's good quality, high fidelity 2 qubit gates. The net result is one, you can submit multiple circuits to one device because it's virtualized, and so it'll be exposed as multiple QPUs, even if it's a single QPU, and run these concurrently without drastically impacting the results of the system. So you can get a real performance throughput increase without actually affecting fidelity. And that's what we're just looking on the right-hand side with those plots. All right, you're ensuring uniformity of qubits in an atomic region and a reduction of crosstalk. And the result is an improvement typically of mean fidelity, and usually a reduction also in the variability of fidelity. So if you think of running, let's say, a 4-qubit circuit, and you submit it to the device, it can be essentially placed anywhere. The device is not necessarily aware of the best placement for this 4-qubit circuit. And so if you just naively parallelize, and so you stick it all in and just hack it up, you can drastically impact fidelity, increase variability. But even if you don't pack it, you just submit the job over and over again. You can look at the variability of that run. And if you just use, for example, an IBM device like Kingston, using Qiskit, you can get quite large variability of essentially job-to-job variability, whereas DynQ, because of its atomic region and tries to identify regions that are high quality, reduces that variability while also typically just increasing the mean. But there's a good reduction in the variability, but it also enables that job parallelization without drastically destroying the fidelity. So if I look at the number of batches that are run concurrently, you go from 3 to 8, and the average fidelity stays flat. So there's no change as you fill up the device. So you can, in principle, think I'm going to be worse off because there's going to be crosstalk is going to impact more of the various qubits. But in this case, because of the community detection, that's not the case. And so you get a pretty reasonable, steady fidelity as you increase the amount of throughput with some moderate variability. Now that gets to the virtualization of the QPU, but how about integrating the QPU into a real-world workflow? So if we look at bioinformatics in this example, the AI also is a good example of this. They can make use of multiple tools with different computational resource requirements running on HPC systems. In this example, it's a bioinformatics workflow. It's orchestrated by Nextflow. And the end result is that though it looks like many possible steps with some complex interdependency, essentially the real world problem is where you're going from green to green, right? You want to have a bunch of input gene sequence snippets and come up with a report of the genes present, the confidence of those genes in terms of the analysis. And through this process, each job will run at different points, but also at different necessarily computational footprints. And the interdependency is quite complex. So if you wanted to think of accelerating a portion of the workflow, right, you might accelerate a specific tool, same way you might accelerate a specific portion of a code, and you want to stick in a quantum computer in this context. So let's consider adding a quantum computing accelerator to this workflow, right? Maybe some portion of Kraken has some quantum circuits to send. It still may want to do other tasks at the same time, but also other tasks will want to run asynchronously as well. And so you may submit a circuit, but we are in the NISQ era, right? So quantum computing devices are noisy, are not necessarily stable, so they don't necessarily have the best uptime compared to especially classical computing. There could be quite a long queue because they're scarce. There are very few quantum computers out there. So if you're submitting to quantum hardware, you're competing with not just a few people, but essentially a bunch of people globally to submit to that system. And what happens if you need to iterate? What if you want to do error correction? What about optimizing a circuit for a given hardware? And even batching up a bunch of jobs. So perhaps there's a few different tools here that all want to submit different quantum circuits, but possibly also the same QPU, and they don't necessarily want to get in each other's way. So you may want to batch it up, which is where DynQ comes in. But let's consider just the integration aspect here. We want to have quantum supercomputing, or more appropriately, superquantum computing, right? The idea of integrating a quantum computing as an accelerator to a supercomputing environment. But there is a mismatch. Again, so supercomputers are exclusive access to a portion of a supercomputer for a specific amount of time. You access that through job schedulers, and resources are typically readily available, right? And you can retry without issue too much. Quantum computers, right? It's dynamic shared access to a single resource, right? And they usually access through cloud-oriented APIs, but the idea is critically here, they're scarce, right? So we were looking at this and trying to say how you can enable scientific computing with a workflow-oriented approach. And we developed QBitBridge, right, which is using, it's an open source workflow framework built on Prefect and SLURM. It makes QPUs look like just another resource, like CPUs and GPUs. And why it matters is it really does break the barrier of accessibility, right? You can have scientists focus on writing up the workflow, writing up maybe a little bit of glue, but not much. And so they can focus on not necessarily the challenges of making use of a QPU, but just putting a request to use a QPU. This has been tested today on superchips, virtual QPUs, also QPUs. It's got AWS Bracket as one of the interfaces, Qiskit, QR blockade, right? IBM's Qiskit, and is ready for more hardware to have direct access. Now, the idea here is, I'm going to show a quick movie, is to enable essentially multiple QPUs and multiple GPUs and CPUs. So this is a multi-QPU workflow where a job is spun up to receive circuits and submit circuits. So it takes like one core. And they're these essentially launch vQPUs. And once they register that a QPU is available and can accept circuits with the appropriate authentication, they can then say, I'm willing to receive circuits from any other service. You can run stuff on a QPU. So this is running a Bell state. You can actually dynamically investigate as the job is running, how the system behaves. We're going to be adding in calibration setups for any circuits that people do submit, so they can demand that calibration be run before and after a circuit submission if they definitely want it. There are multiple GPUs being run at the same time. Everything is being dynamically constructed, right? There's not like a well-defined DAG here because it's all dynamic, asynchronous, and then the workflow is done. And so this is about melding both QPUs and GPUs and CPUs into one workflow. So how are we enabling quantum computing, this hybrid quantum classical computing? Well, we're simulating QPUs, we're abstracting QPUs, and we're integrating QPUs with HPC. And with that, I'd like to thank you. And though I can't be there in person, I will be there online to answer any questions. Thank you very much.
Sure if we have Pascal online to ask him some questions.
I am here.
Oh, look at this. Hello. Yeah. Thank you so much for joining. What time is now in Perth?
It's just 3:30 in the afternoon. So I mean, it's just a little past 3, like close to 4.
Awesome. Thank you so much for joining this at this time. Do you have any questions from the audience? If not, I have some for you, but so, well, in the meantime, while the people are warming up and they're thinking about the questions that they want to raise. So how many people have you fully onboarded in the Quantum Bridge that you have in Pawsey Supercomputing Centre?
So at the moment, it's basically one major project that was looking at turbo machinery. So they were doing CFD simulations. Hold on, me getting an echo, so I'm going to mute myself if I can. But you guys can still hear me. Yeah, it was a CFD simulation group that we're looking at trying to do quantum machine learning. And so we basically adapted some of their workflow to do the QML plus also all the simulations at once, which was kind of cool because we ran 65,000 sets of simulations while doing quantum machine learning. We are looking now at onboarding also a group doing 3 different groups doing quantum machine learning and chemistry. So they're each focusing, 2 groups focusing on chemistry, 1 focusing on machine learning workflows for oncology, so for cancer treatment and looking at doing the diagnostics for image processing for cancer, plus also then doing some quantum machine learning. And the idea is to offload onto initially virtual like simulators, so essentially the vQPU. But then we're going to move to, they're going to try through Bracket a couple of actual real QPUs. And the same thing applies for the chemistry workflow, where we're probably going to make use of DynQ as well. because we can probably pack a decent amount of the initial variational algorithms by doing that job packing. So we think we can probably speed up the throughput, but using QBitBridge to then chat directly to DynQ to submit circuits to that service that then chats to probably a couple of the devices on Bracket to push the throughput.
That's awesome. So if another supercomputing center wants to build something like this, I guess that building this community awareness and get that community to get ready to use this infrastructure, it will take a while. So how are you dealing with this? Are you providing ongoing training, or it's more kind of an ad hoc and you work with them till they get success?
Yeah, so for the community, for the research community at least, we have specific sort of uplift projects called Pulse projects. And so it's targeted training for specific groups so they can be beta testers, but also give us feedback, but also help them do the science. And then in terms of growing the community on the sort of development side, so for QBitBridge, for a couple other platforms, everything's open source because that's how we roll. We like open source. And we're trying to make sure that we adapt. So we work with and collaborate with groups, centers like there's an active collaboration in Japan with ACE, and a collaboration in Europe with Lynx and Chineka to try to run the software on their systems, but also adapt the software so the meshing is a little better, so we can handle stuff besides, let's say, SLURM, or and that's why we also really went for that GPU or GPU ecosystem agnostic simulators, so that in principle we can get performance on AMD GPUs and also on CUDA GPUs. There was a recent update today that my team and I, Shusen was rebuilding the quantum simulator with a new version of CUDA, and we beat Qiskit Air. So we're doing faster than the Qiskit Air. But the idea is to grow the community, trying to provide a bunch of portability in the code base, and also train users to make use of it so they can write workflows up. So we've got a couple of different avenues.
Thank you so much, Pascal. We have time still for more questions. Coming.
Hi, thank you very much for the talk. I was curious about specifically the batching up jobs for executing at one time on a single QPU. You put an image of the IBM connectivity.
Yeah.
I assume that when you do that, you were mapping areas with minimal crosstalk between them of the chip, but I assume that if you are sending more signals, you are doing more stuff with the chip, there will be some crosstalk. So there must be a trade-off between the use you get of a given time on that QPU and the quality of the measurements that you perform. So what's your criteria? Has been done this already on real chips? And if so, what's the criteria for dealing with this trade-off, if it exists?
Yeah. Yeah, so that is actually from real hardware. So both the community maps that I showed were from built on the calibration data at a given time period for Kingston and Anka 3. So the IBM maps. So those are real world community maps. Like that was actually run on the hardware. And in this case, what we do, we have an aggregation to try to minimize a couple of different metrics, improve. So you basically take 2 qubits as your first startup community discovery. So you look at the neighboring qubits that can be added to that community. You check if adding the next qubit and the fidelity measurement of the 2 qubit gate plus a couple other fidelity measures like single qubit gates and so on, doesn't drastically decrease the average community quality, I can point you to the paper. And so the idea here is that we do a community discovery, kind of a greedy algorithm, grab what we can, and fill up a community till we reach a point where adding any of the qubits on the boundary would decrease the quality of that community significantly. And then we stop and we start a new community. So that's run on real hardware. And so there is a trade-off, right? But the key thing in that batch placement is it was pretty minimal. Like, I mean, the variance that you see per batch, so a batch size of 3 wasn't 3 that filled up the entire QPU. It was just a batch size of 3. The circuit size was actually much smaller than the QPU and was smaller than the average community size. So it was just there. So there's a performance trade-off for throughput. But the idea here is that if you think of, let's say I'm going to throw IonQ in this, but they have different connectivity. It's quite expensive to run on some of these systems. So if you run one shot with 2 qubits, okay, they still charge you full usage. But if you can be like, no, I'm using all the qubits, I'm running 6 jobs at once, then you're really also decreasing the cost for researchers. But in this case, Pawsey, we provide access, but it reduces our cost for running stuff on quantum hardware. But it's not just about also job parallelization. We can try to aggregate several different jobs. That works, but I don't know how well it's going to work. So we don't have a massive set of users all submitting to the queuing system we've got to then propose the new circuit that's then actually sent to the QPU. There's also challenges that I didn't mention here, but like confidential computing is a quite challenging thing even classically, but in this case, it's a bit more challenging even quantumly. Though it's, in this case, it's not like your job will be unknowingly negatively impacted by the fact that it's running with other jobs. It's a pretty minimal impact, but that's the key thing we do. We do a bunch of testing as well. So there is some of running DynQ. It does obviously take calibration data, but then does some polling to see if there's drift in the calibration data. And we are still kind of fine-tuning some of the ways to better aggregate communities. Because basically, we chop the QPU enough to make sure that we kind of meet some threshold. But if your circuit was bigger than the number of an atomic region, the maximum set of qubits that have said to be good fidelity, you then need to figure out what's an appropriate community to grab to merge 2 communities to then run the larger circuit. And there's a naive thing that we're doing, but it kind of works, but there's probably some more improvements to do. So I feel like we can probably reduce that variance down that was in that plot, but the fidelity stays pretty good. So that is from hardware. So that is not like simulation. That's purely just actually submitting stuff to Kingston, I think.
Okay, thank you very much.
We still have time for one more question.
Hi, Pascal. Hope you can hear me. My question is related to the previous one. It's nice to do all this parallelization, but you also mentioned segmentation with your compiler thing. And I wonder how that works in the computer engineering point of view, because in order to segmentate, you need to have a clock, you need to have a memory with states, you need to have these sort of registers and everything has to be properly orchestrated. I really wonder if qubits work with the same laws of nature that normal processors do in this case.
So in this case, the circuit partitioning, right, is that you can decompose the circuit into 2 separate circuits that can be run at any time, and you basically do some sampling. There's some overhead to running it so that you can reject certain sets of results and stitch together. So it's not like we're trying to do distributed quantum computing, though I do actually have some work that we're trying to do on distributed quantum computing, where you propose a circuit where there's an entangled Bell state that acts as the binding for 2 local circuits. But in this case, you're running several circuits together, which cumulatively, once post-process, can produce the same result as a circuit. Now, this doesn't always work, right? So there's a lot of overhead in also doing this. But it's one of the ones where we feel like it allows, if we can get it to work well, and we're still trying to work on there's research algorithm, like research to do on the actual methodology of circuit partitioning and circuit knitting. How would you want to do in terms of checking to see if you can split a circuit, and then what type of post-processing you need to do to make sure you've got the circuit. But past that point, in this case, it's asynchronous. So the idea is that I don't need to coordinate results. I get a result, I get a swath of results, I get a swath of results for circuit 2, and I post-process. And then you get what could be an equivalent of running a larger circuit. But there is more overhead. You have to do more shots, definitely.
Oh, okay, I see. Thank you.
Okay, so because we have still time, so I'm going to ask you one more question, Pascal.
Sure, go for it.
So I love the strategy built around Pawsey Supercomputing Center, because you don't need to have actual hardware or do massive investment to have a quantum computer in place to expose this capability to your user community. But I was wondering how you are dealing now with the second big challenge is the finances of getting access to this external resource. So how are you dealing with the budget and grants or the mechanism that you are using to expose this capability to the users?
Right. So one is the fact that we did get a grant, and that grant was a national grant that explicitly asked us to investigate integrating quantum computers and see if we can provide services to the user community. So that grant was then used to essentially buy time on cloud accessible quantum systems, and then the major bit of work we've actually done is to set up an interface to AWS Bracket, where we have budgetary controls. So AWS, for India, there probably be some AWS people there, they don't mind charging you more money, right? But we want, saying we set up a project and it has a fixed budget of $10,000 over the course of the year to do quantum computing experiments, then we really want that budgetary control to be in place. So we've set up stuff as well to provide free access, where we have a merit allocation scheme, and we know how much the budget we have, so they can't exceed any budgets. We're not worried about overflow. We're just saying, okay, we know we have got set aside $100,000 over the course of the year to split up across multiple quantum computing projects, and they propose merit allocations, right, like they do scientific computing. So it's like, Horizon PRAISE programs, all these things where researchers say, we've got a science question we want to answer, and we need this computing infrastructure, and we need this much of the computing infrastructure to answer that question. So that gets reviewed by other scientists. We check the technical merits, and then they get an allocation, and that allocation has got a fixed size. So it helps us not worry about budget blowouts. We can plan ahead, and we can say, we know we're going to offer this much. Now, there's a huge variation in the cost of different quantum computers. That is a bit of a challenge, but we try to provide access to a wide variety of technological modalities to have people who don't really care about connectivity be able to run on larger superconducting systems, but maybe also people need really complex connectivity. There's an all-to-all entanglement, and they want to run on an IonQ system or a neutral atom system. So the mechanism is research grants and national grants, along with partnerships with other research institutes to see if we can also access hardware that they've provided by also providing software expertise to do experiments so that we can enable other supercomputing centers. So if another supercomputing center had a quantum computer, this is something we're looking into, but if we had an on-premise quantum computer, the idea would be not to limit it to ourselves, but see also if we can reach out and give access by also gaining something in return, expertise, access to other computing resources. So there's an exchange so we can grow the ecosystem. I really feel like we should try to make sure that it's very collaborative and open, because that's the way to kind of grow the ecosystem so that you get new technological innovation.
Awesome. Thank you so much, Pascal. So please, thank you, Pascal, for your time and for participating in this event.
Wish I could be there.
Thank you.